All right, I'm back. Took a little break this afternoon. As I mentioned before, sort of nearing the end of the project. Just wanted to talk a little bit about kind of how I felt like it's going. I know I still have 2 more days left, Monday and Tuesday. I don't know. I still haven't decided whether I want to do anything over the weekend. I might, but I might also just take it easy. I'm not sure. So reviewing the project. I think overall, if I had to kind of evaluate myself in this project, that this was a big kind of like level up for me in practicing a lot of the basic calculus and math skills. This isn't to say that I haven't learned any of these things, but it's just a kind of +1 for that process. And because it's a +1, it's harder. And not only is it harder, it's requiring me to refresh myself on a lot of these things that I learned, 7-8 years ago. And so this kind of thing is, I think, a pretty common situation that you learn some things, a long time ago, and then you want to like do something, maybe I'll give an example. Maybe you did some high school math and then you went off and you did something else and you never did high school math again. Then you want to learn some kind of college math or you want to, go into that field, but you can't remember anything. It's been so long. It's hard for you. And so there's a lot of relearning, there's a lot of building things. And it's very easy, I think, in those moments to feel insecure, to feel like you don't know these things, that you're not good enough, that you should know these things. And I've definitely felt some of those feelings when I've been going through this because, it's like, oh, right, I should know this. It's not coming in. And it's just because I haven't practiced it. And I've been a little bit out of practice. That being said, though, this past month has been a really good practice for getting kind of back up to speed with a lot of these, advanced math techniques in calculus, differential equations, physics, electromagnetism, complex numbers, all these sorts of things. And so I feel good about having gone through that process because it's been a while since I've done that. And that would have been necessary if I were to do this project anyways. I could have done it where I just went back and redid those classes. I think that would have been maybe more comfortable for me to do that. But it also probably would have been a lot easier too. So it would have probably taken a lot longer because I would have had to go through all those classes again. So I do like the way that I proceeded through this class, although the amount of having to get caught up and relearn definitely slowed me down compared to if I were just doing this from the start. And in terms of getting an intuition about quantum mechanics, I feel like I've understood a lot of things, but there's also a lot of questions that remain unanswered or things that I haven't quite figured out yet. So maybe I'd like to just take a few seconds right now. I do still have one more problem left on my to-do list, so I will get to that. But I think I'd like to just take a few seconds just sort of talk about some of the things I've learned at a very high level. This isn't going to be my final draft of things. I did kind of want to wanted to do like some sort of, this is what I learned in this project summary at the end of it. But I think I'm going to edit that a little bit more because, this is doing this live. I'm kind of going back and forth and doing these kind of things. So what I'm going to do is I'm going to talk about some of the things that I've learned in the last month, basically, of learning quantum mechanics, and some of the questions that I still, I have some idea, but I still don't have that answer to yet that I'd like. So I'm going to just switch over to this view so you guys can see it. And I'm just going to do this for a few minutes. I'm not going to do a full thing of like every little thing that I've learned. So the first idea I would say is that what is stuff really? So this is what quantum mechanics is all about, is what is the stuff that we are talking about? What is the world really made out of? And the idea that we have been presented in this sort of class or with quantum mechanics is a model. I don't think, some people say that they want to have an intuition about things, and I think it is possible to have an intuition about things. However, I think it's a profound fallacy to expect that things should be intuitive in terms of your everyday experiences, that in order to be understandable, it should be something related to your everyday experiences of things. For instance, that what's the visual picture of these objects? Well, there may not be a visual picture because vision itself is involving like shooting, photons off of things. And so when we deal with things that are the scale of photons, it's a little bit like what's the color of a hydrogen atom? Well, it maybe doesn't have a real color, just like the way that a macroscopic object does, because it's just this small little thing that like the actual wavelengths of light are about the same size. So it doesn't maybe make sense to ask what the color of it is. In the same way, it may not make sense to ask what is the visual picture of an electron. All we can really say is, what kind of properties it has, what sort of model it has, and to build an intuition of that, just the same way that you might build an intuition of economics, even though economics is not something inherently visualizable, or you might have an intuition about, would be another example, an intuition about, I'm trying to think of another example of something here, but like of some sort of process that you might want to know. So this is what quantum mechanics is. And what can we say about quantum mechanics? Well, basically, I would say that we have two things. We have a wave function, and we have measurement. So first, the wave function. So this idea is saying that we can kind of represent our stuff with a wave. And so let me just draw like a wave here. So let's say this is, this is our stuff, right? Get a wave. Now the difference between this line that I drew in quantum mechanics is that quantum mechanics has two values. So this here, everything has just one value. Every point just has how high it is up here. Whereas in quantum mechanics, there's actually two values for each of these. It's a complex number. So to say it's a complex number is a little bit like saying if we drew it they can imagine this is a three-dimensional thing. And we can imagine these arrows and they're kind of rotated. I mean, it doesn't look very good when I do it like this. All right. So this is our wave function. It's if we're considering a one-dimensional system, it looks like these arrows rotating around on a particular point. This is our wave function. And so the first idea about the wave function is just like regular waves, you can superimpose them. So if you have some string and you kind of make this wave, and then you make, let's say, this wave, and then these waves, let's say they travel together, then in the center you might have, I don't know, some kind of horrid complicated thing like this in the center. So it might be really confusing, but it's just made of this wave going this way and this wave going this way. And because of the properties of waves, that these kind of things are linear, you can just add them and you can treat them as kind of almost separate objects existing in the same wave. And so similarly, because we're dealing with wave functions, which is almost the same as this, except it's rotating. It's not just going up and down. You can do the same kind of thing. And so the math is such that, this is, again, a horrid complicated thing. And this maybe is a really complicated thing. It's really hard to make predictions about it. So what you can do is you can consider, well, instead of thinking about it in terms of just one wave, we can thinking about it like with our individual waves added together. So there's a bunch of different ways that we could add it together. So one of them is to just imagine we could just have a bunch of single, like really thin peak waves that are all adding up, and they just have a height equal to the value of this, right? So this could be one kind of wave, one way of building it up, I guess you could say, building up our wave like this. You could also imagine just making it out of sines and cosines. Or I mean other functions as well, you could make it up out of. And if these have some sort of tractable properties, it might be easier to analyze how it works. But again, you can just sort of think of that as sort of a mathematical convenience because you really have something like this. It's just some kind of wiggle. Now, I think it's important to realize that this looks two-dimensional, what I've drawn here, and this looks three-dimensional, what I've drawn here with the arrows sort of rotating around this line. But the arrows don't actually go into space. They're just a value. So this is actually just a one-dimensional system. So this arrow pointing is just a mathematical convenience. It's not actually pointing anywhere. This is just a line. And similarly, so when we move up to 3 dimensions, well, every single point in space has this kind of 2-dimensional arrow attached to it, of which direction it's pointing and a length to it. But I mean, it's filling all space with these little points. So now it's impossible to visualize, because now you got to imagine every single point has a little arrow that's not going in 3 dimensions like the space around it. It's only going in 2 dimensions. So, I mean, I don't really know how to draw that with pencil and paper. Maybe if I had a computer program, I could make something that looks sort of. I was thinking about that for a while. Like, what's the best way to make an analogy when you get up to 3 dimensions? And I was thinking, well, maybe you could have like every pixel or little like 3-dimensional pixel voxel of thing is like has a kind of transparency according to the length and like a color. But I don't know, that was sort of not really helping me, because I think it's easy to imagine like that these 2 arrows cancel each other out because they like one walks the other back. But I mean, what does it mean for like the color of a voxel? Like, I don't really know, right? But we can just, you can just sort of imagine that that is what the wave function is. That it's some 3-dimensional thing in 3-dimensional space, that every single point has this arrow. And one of the things we know about the arrow is that because of the Schrodinger equation, what we know is that these arrows are just kind of rotating. So in time, they're kind of rotating like this. But of course, it's not a stick like this. It's just an infinitesimal point, but the direction it's pointing is rotating. So that's the wave function. And what happens when we measure the wave function is, because it's not, so if it were just waves, if it were just that, the world is made of waves, I mean, maybe the math would be complicated, but it wouldn't be too confusing. That's just sort of, that's just the math, right? What the wave function is not a wave of stuff going, but it is a probability. This is a probability. And so when you measure something, what happens is the wave function, what's called collapses. So if you were trying to measure, let's say this is our wave and it was like this, and we were trying to measure the position of something. Well, because this is a bigger arrow, it's more likely to be here than here, let's say, because this is a smaller arrow. But that's basically what the picture is that we don't, it's not like it's a bit here and a bit there. It's that it's only in one of these points, but it's more likely to be here than it is to be there. And so that's if we're measuring position. And if we're measuring any other thing, so if we're measuring, let's say, the momentum of it, so we're measuring like how fast it's moving, then instead of like collapsing down to a point like this, we're considering what it's going to collapse into one of these sines and cosines. I'm trying to think of a good way to explain this without using math, but basically you can make any function out of sines and cosines, just like you can make them up with little points at that, at every single little place. You can make it up with an infinite number of sines and cosines. And so if you wanted to measure the momentum, you're basically asking, what is the, how many of these sines and cosines are there? If that was the question you're asking, momentum. And so if we're asking that for this picture, we're just saying when we measure it, we don't see that there's like these infinite number of sines and cosines. We only measure one of the sines and cosines. And same thing with energy and angular momentum and all these kind of things, is that we just measure one of these states. And so this is the sort of interpretation of the wave function. And this fact that we have this wave gives us a lot of physics of the world. So one of the physics situations that you can find is that the electron orbits are discrete, so that it's not the case that the electron just orbits the proton in a hydrogen atom willy-nilly, kind of the way that the planets orbit the sun at random, like very specific. Mercury doesn't have to be exactly there; it can be at any position. It's just sort of chance where it ended up. Whereas we know from chemistry that, hydrogen isn't like that. There's a very specific energy level that is the sort of lowest energy level that is held by the hydrogen atom. And this comes out of the fact that when we imagine this system, it is made out of these waves. And so the math is a little bit complicated, but essentially it's for almost the same reason that when you have, let's say, a musical instrument. So let's say you're blowing air across a jar that has a certain amount of water in it, that it makes a very specific tone. It doesn't make all types of tones, it makes a specific tone. And that's because this happens to correspond with the number of wavelengths of the sound that you can fit in this thing, so that there's a certain resonant wavelength that matches up with this, and all the other things just get kind of died out. Now, this is a little bit not quite the right picture for this, because we're dealing with a very fundamental thing. So it's not exactly like this. This is obviously a composite thing. So sometimes you get a little bit of sound and a little bit of a different thing. But it's kind of the same reason that you need to fit the thing into the shape. So if you can imagine, it's a little bit like it's a three-dimensional bottle, but it's a little bit like fitting it into a bottle. And you have to have your wave function can only have certain kind of harmonics, just the same way that this can only have certain harmonics fitting in the bottle. So that's something you wouldn't have expected from the classical picture of things that makes sense, because we're dealing with these wave functions. And that's almost sort of just because it's a wave, it follows from that. And similarly, if you can do a bunch of work, but if you do it for like crystals of things where you have a bunch of these little, it's some kind of rhythmic sort of structure, you also get sounds, except instead of being perfectly discrete, you now have this kind of range of sounds that you can have. And the distance between these sounds kind of indicates the properties of it, so that diamond, for instance, is clear because the distance between these things is larger than the wavelength of visible light. So visible light can't disturb it. It just goes straight through. And there's a bunch of more properties like that you can get from this quantum mechanics of it acting like a wave. So the wave nature of it is, it's again kind of complicated mathematically, but it's not, I don't think it's too hard to imagine that the world is made of these little wave-like things, and that the hydrogen, the electron that orbits around our molecules, is kind of, it's stuck at a certain level. It can't go down too far because it has to fit, like the way that the sound has to fit within the bottle. When you're blowing across it and you're hearing a specific frequency, that it has to have a certain frequency because it has to make that sound, that sort of resonant frequency. It's a similar kind of idea. The things that I don't quite understand, so the things that I would say I'd still leave out of questions that I have remaining, is the way it's been kind of discussed in the class is just that we have a measurement phenomenon. So we're doing this act of measuring, and in doing this act of measuring, it's said to make this sort of thing collapse. Now, I know already that this isn't entirely true, because you can measure something to different degrees. It's not something like measuring is this binary thing that you plop down onto the system. Basically, like if we wanted to measure, did the electron go through here, we can make it go through a slit, and the tighter we make the slit, the better we have of saying the electron went through this particular slit, right? If it's a fairly wide thing, we haven't really measured it to that much precision. If it's extremely narrow, we've measured it to a great deal of precision. And so that's a little bit like saying, taking our wave function, and let's say our wave function was like this before, looked like this. And if you push it through a very, very narrow thing, maybe now it comes out and it's like this. It's just become very narrow. So I think I can understand this kind of position momentum trade-off, that when you've made it look like this, well, now to build this out of sines and cosines, you have to use like a lot of them. There's a big spread for the sines and cosines, so it kind of shoots off in all directions after you measured it there. But I think that some of the things that we're talking about where, for instance, you have, let's say, an electron, and then the electron gets shot off, and then there's some kind of reflector, and then we have a detector here, and then the detector does something so that we can read, was there an electron there? And what we know is that if we had, let's say, two detectors, so there's maybe one here and one here, and we shoot it one electron at a time, we only ever get one here or one here. We never get two or a half, or it's always a discrete kind of phenomenon, which isn't how regular waves work, which is why we interpret this as being a probability. But I guess one of the things that wasn't explained as clearly in the class, which I would have liked, is what are you doing when you're doing it here, which forces it to kind of pick a side of which one it went through of a probability. What is the thing that's happening here? And my intuition about it is that what is happening here is that when, let's say, this caused the wave to split up a little bit. So again, if this were just waves, that makes sense. So we've got maybe some amplitude here and some amplitude here, and maybe it's bigger here than it is here. And then this amplitude, let's say it does something to whatever is in the detector, and it matches up, and then it gets sent through, and it goes here. And then this amplitude is set up in this detector, and it goes through and it goes here. But the idea being that when all these amplitudes, that this kind of basically entangles itself with everything in the detector here, such that if you see it here, so if this sort of, this macroscopically gets up to the detector, then it won't be here. It won't macroscopically be up in the detector. So you have kind of two states, one where you saw it here and one where you saw it here, and these kind of have some sort of amplitude. But if you saw it here, then you can't have seen it here. So, and that's how so this sort of process, I think, was not really done as much in the class. And it was, I think, probably just because this is the first class and there's a lot of phenomena that were just started to be introduced, things like spin and angular momentum and stuff. So there just maybe wasn't time to really cover it in detail. So this is something that I'd like to cover in a future class, is to sort of understand this in more detail, because I think this is kind of like, you get a wave function and then it collapses into one of these eigenstates that correspond to something that has a definite value. And then we have some probability of collapsing into that state. What is it? What kind of properties, physical properties of this detector allow you to do that? And I think one of the ideas that I've heard that was not from this class has kind of been proposed, this many worlds idea, is just basically that everything just gets entangled here, so that these, like, let's say you saw it here with this amplitude, this is all getting kind of locally consistent with this, and this is all getting kind of locally consistent with this, and then you're looking at it, and so you're also getting kind of entangled, and everything in the whole world is getting entangled with this, whatever thing happened here. Whereas when you deal with the electron, and you're not amplifying this up to this huge scale, it's staying in this kind of coherent state, and so you can do things with it. So I think that's sort of the part that that wasn't explained as well as I would like, because they talk about measurement just sort of, I guess, the physics of what's happening when you measure something, I think, was not made as clear as I would have liked. But the mechanics of quantum mechanics, if I can say that, I think are a lot more clear. And I think it's just sort of interesting to think of this wave function. Oh, I folded this over here. This wave function in terms of, in terms of basically being like probability, but instead of just having one value, you've got two. So you have little arrows, so they can, you've got them. The length of the arrow is how likely something is, but you can point them in the opposite direction and have them cancel out. Whereas for regular probability, you can't do that. So that's kind of interesting, right? That's what stuff is made of. I think there's a lot of I think that there's a lot of stuff that if the world were just made of these waves, it's just made of waves at the basics out, or even complex valued waves. I mean, that's complicated to think about. It's hard to visualize that maybe, but it's not so crazy. I think what is confusing is how, when you do this measurement, like the thing I just described, when you do this measurement, it turns into something else. And I think that's the part that I would like to have understood a little bit better, that they didn't explain as much in this class, is like what's happening here, so that it was this thing for all intents and purposes, and then you measured it and it became this thing, or it became this thing, or it became something else, right? So I think that's something that's going to have to be saved for a later class. It's a little unfortunate. It was something that I wanted to was hoping that they would discuss and go into more detail in this class. But I'm still happy that I went through and got a good grounding in the math, because I'm not talking about this in a mathematical way. And of course, if you're good with the mathematical structure, you don't have to be kind of loosey-goosey with it. You can kind of say, well, this is exactly what it's going to be, supposing you can do the calculations, because they're often quite difficult. So with that little digression aside, I'm going to continue working on 10.7. I think that's going to be it for me and this project, for working on it, at least for right now. And then I think Monday and Tuesday, I'm going to just work through the exams and just use that as a kind of evaluation to see how far I got. And then after this class, I don't think I'm going to extend it. So I'm not going to be, continuing to live stream, continuing to work on it more and more and more. But what I will do is I'm going to probably in my own time continue working on these, continue asking some of these questions. And now that I'm equipped with some of the math, I'm in a little bit of a better position to understand some of the answers of why this is doing this, or what's the right way of thinking about it. And I'd like to keep digging deeper. So I think I might start doing the lectures for 805. I might do 805 and 806 lectures. I don't know whether I'll drill into problem sets right away. This has been a pretty serious effort getting up to doing the problems in this one. And so I think for 805 and 806, I might just sort of see what they're covering and then pick and choose what I want to study, rather than do the complete classes like I've done here. So I guess I should get back. Where did I leave off in 1007? Let me just get back over here. So I just did C, which I remember being very confused because we had this E gap, and it was like, I don't know, the energy gap. Well, first I did a real stupid mistake, because I was making this horrific calculation, and it was all because, where did I do it? Where's my C here? Oh no, that was part A that I didn't do it. This one here was, I didn't think to Taylor expand it. I was trying to do small angle approximation. So here I might as well just do the part D here, because it's going to be all related to it. So we have our cosine, so cosine n pi plus E over root T. And we're going to Taylor expand around this E. So this was the thing that was kind of bothering me a little bit, is that our KL here was just epsilon, but our energy is an order of K squared. So when they got this epsilon is equal to this root T, I was like, well, but that's not a difference in energy. It's a difference in the square root of energy, or, so anyways, that kind of annoyed me a little bit, but I'm not sure. I'll just do this the way it is right here. So if we were to Taylor expand this, again, we have our cosine n pi. Oh, what we're looking at, bands. So this is supposing they're very strong. So now we're not looking at this as n pi. The bands themselves are going to be at m pi plus E. It's not going to be n pi by E. It's going to be m pi by 2. It's going to be same thing, but n pi by 2 or over t. And so we have okay, now this time we have the opposite here. So this one here is going to be 0. This is also going to be 0. Oops. I shouldn't remove this e here. It's also going to be 0. Well, where did I get? Oh, yeah, here. These are going to be 0. So we're going to only have these signs here. So we're going to have our, and this is going to be 1s. Where do we have it here? So e. Minus or plus, this is going to be e cubed over 6. E to the 5th over 5 factorial. What's 5 factorial? 125? No. 6, 24, 5 times 24 is 120. Like that. So I think, and then this is equal to what? So I think this is how we get our e is roughly equal to root t, because this is equal to 1. This whole thing is equal to 1. And we've Taylor expanded this. I'll just put this over root t. Get root t is equal to this. I don't know how we got rid of the plus or minuses. But yeah, that would be my answer. All right. All right. I will leave it at that. Now let's go to part E. For Vx, a delta function bearer with g naught greater than 0, use previous results to show that the cotangent of phi is equal to 2kl over g naught. T equals cosine squared phi. Hmm. Well, let's open up problem 5 and solution set 7. Just so we can get the results. Where are we? So this guy is equal to arctan imaginary t divided by real t. Ba, ba, ba. mv naught over h bar squared k. What is our g naught for a g naught for this problem is going to be? What are we trying to show here? 2kl. Oh, where do we get the L from here? 2klg naught. So we need to have 2 of these guys, right? Where's that problem? This is just a single one. Ah, okay, here. Potential made of 2 of them. All right, let's go down to D and E. So hold on a sec. So phi is going to be equal to 10 minus 1 of, I'm just going to write it in here. Yeesh. What is our little t? Let's remember ourselves what S is. S is going to be R T R T. Is that S? Oh, TR. So we want the bottom one here. So we're going to have, oh, lovely. It's not loading everything. Okay. Hopefully this is right. H bar squared K over M V naught squared. E to the 4 I K L minus I H bar squared K over M V naught plus 1 squared. This is our phi. We want to show the cotangent of this is equal to this. So there was an identity down here. Okay. So we can also do cotangent minus 1. So cotangent of this is equal to e to the 4 IKL minus I r squared K over MV naught plus 1 squared over r squared K MV naught squared. Oh, wait, it's not this. It's real, imaginary of this divided by real of this. Hold on a sec. So hold on a sec. I'm going to go phi is equal to and we can change this easily to cotangent, and then we can put the cotangent over here, so we can have cotangent of phi is equal to, and we'll just switch the real and the imaginary. All right. Okay, now we're gonna just do a bunch of math to cancel this off. All right. Up top, this is going to be purely real. I think we can cancel both of these. Right? Should be able to do that. And then because we can flip them around again, so we should be able to get imaginary of imaginary part of this is going to be our sine 4KL. And then this is, well, we're going to have minus our h squared k mb naught minus, and that's actually going to cancel because this is real. And then we're going to have two of these because it's I times this is 2 minus 2 h squared k e naught, and then the 1 times itself is also going to be it's 1, but that's also real, so that's going to cancel. And then we're going to have here, we're going to have our cosine 4KL, and this time this is going to stay. Going to be h bar fourth k squared over mv naught squared. And then these ones are going to cancel. We're going to have our plus 1, right? Well, this isn't canceling in the obvious way. Am I starting with the wrong place? I mean, we got to do this one, right? Otherwise, we don't have the L. Let's see what they do. Question is E. Single delta function. How do we get... Oh. So they're not using the 2 problem one. They're doing... Hmm. Okay. So they've just done times 1 minus I G naught over KL 1 minus I G naught 2KL is equal to I G naught 2KL divided by 1 plus you just go 1 plus G naught over 2KL squared. there's actually quite a bit of trig here going on, and I have to pay attention to this. So okay, we get this e to the minus I phi. How did they get that over? How did this? I'm not sure how they solved this. Hmm. So cotangent of phi is going to be equal to cosine phi over sine of phi, which is going to be equal to I can do cotangent of phi is equal to, let's just do so what's the real part of this? It's 1 over 1 plus g naught over 2 kl squared. Imaginary is going to be just g naught over 2 kl. So we can flip these around. So we're going to have 2 So all this is going to be, let me just do this up here. We're going to have if we flip it, what do we get? If we flip it, we get g naught. Multiply everything by 1 over g naught. We have working out. Man, I'm missing some kind of trig identity here to get this one. Well, what do we also know about sine? We have cosine. Let's go cotangent of theta is equal to what? We have e to the other things can we work with to build this up? What are our, let me look at my identities for cosine again. I think I just have the hyperbolic ones. No, I think I have, no, I have it here. This is an exponentials. Where is it? Cosine as exponentials. Maybe I only put, yeah, maybe I didn't put, I just put it for, Yeah, I can't figure this one out. What am I missing here that will allow me to do this? I guess what we're saying is cotangent of phi is just equal to one second, let me just think about this for a second. We have t is equal to this. And it's also equal to this. Yeah, I can't figure this out. All right. I'll put a point in this. I think we're at the end. Okay. That was a little bit of a unfortunate finish. I was hoping to understand all these things, but I there's just some trigonometry there that I'm screwing up. So that is it for the second pass of these questions. So now I have to decide what I want to do. I don't know. I think probably what I'm going to do right now is just spend a little bit of time. I'm going to go through maybe one of the exams. I think I'm going to go through one of the exams that I have that I don't have the solutions for. Think about it and attempt it on Monday, and then I will do the one with solutions for Tuesday. So let me open up the one that came with this class. I'm not going to work on it right now. I'm just going to think about it because that's going to give me a sense of, what should I do more studying on. So let's just look here. I think this is the formula sheet that we have. Yeah. So let's look at this exam again. We don't have, how long would this be? This is closed exam So no books, notes, phones, calculators, 50 minutes to solve the problems. All right, so this is the first exam, just 2 problems. Question 1, psi1 and psi2 are momentum eigenfunctions corresponding to different momentum eigenvalues. Is this also a momentum eigenfunction? No. Different momentum eigenvalues. No. Particle of mass m and charge q is accelerated across a potential difference v to non-relativistic velocity. What is the de Broglie wavelength lambda of this particle? Okay. Two and a half. Well, these are way easier than the questions I was doing. Consider particle of mass m. No. Well, you know what? I might leave this. This is like quite a bit easier. Quite a bit easier than the problem sets. So I might just leave this guy right now. I'm not going to look at these, look at the final exam because I want to try to do it under exam conditions. You know what? I think I might just take it easy for today. I know I have a little bit more time, but I'm feeling a little burnt out right now today. It's been a long week of studying. Last 2 days, I didn't get a ton of sleep. So I think I might just take a rest from Nate now. Might rest a little bit over the next couple of days, and then I'll be back at it on Monday to work through these midterms and then the midterms and final, and then do the midterms and final on Tuesday. I was going to look through them all and just like kind of like check them out, but they seem a lot easier than this. They seem a lot more like the kind of caliber of questions that I'm not going to have a difficulty answering that aren't going to involve such grueling trigonometry and differential equations. Not to say that I feel glad that I worked through this. This has definitely been a level up for me in terms of working through these abilities. But this is definitely a lot more qualitative, shorter, easier problems. So I'm going to take my pause from you right now. I know I was going to study a little bit longer today, this afternoon, but you know what? It's Friday. going to end it off a little bit earlier today. I finished all of this, which, I mean, doing a round 2 of these problem sets is an accomplishment. It's been a hard class, difficult class. So I think it's just good to just relax a little bit. If I have a little bit of time and I want to, I might come online, do some Feynman techniques or something like that over the weekend. But if not, I'm going to just wait over the weekend and get back on Monday to go through these midterms and the final. So again, thanks for following. I will see you in a couple days.